In the previous lecture, I said the plasma have a peculiar property of freezing in the magnetic field. Now, as the plasma moves along, it carries the magnetic field and thereby creates a moving magnet. Before we look into how these moving magnets accelerate the charged particles, it is worthwhile to see how a plasma freezes the magnetic field. So let us consider the scenario where a plasma is moving in a magnetic field. To keep our calculation simple, we assume a situation where the magnetic field is uniform, and in that magnetic field, let the plasma move with a velocity v. To find out the change in magnetic flux in the plasma as it moves along, it is easier to consider a closed loop buried within the plasma, and as the plasma moves along, this loop is also going to be carried by the plasma, and we will find out the change in flux needing to the surface found by the loop as it moves along. So by this, we will know how the magnetic flux in a plasma changes as it moves along. So let the magnetic field density be B. We denote it as B. So now the flux needing through the surface of the loop will be surface integral over B dot ds, where ds is the infinitesimal surface. Now as the plasma moves along, so the phi is going to change, and we want to say what is the change in phi. That is, we want to find out d phi by dt, which is equal to d by dt of the integration, surface integration B dot ds. Now as the plasma moves along, the field is going to change as well as the surface is going to evolve. So the time derivative is going to act on both B as well as ds. So this will be surface integral dB by dt dot ds plus surface integral of B dot d by dt of ds. So this describes the evolution of the surface. Now we know the material derivative d by dt is equal to del by del t plus v dot del. Therefore, dB by dt I can write as dB by dt del v by del t. Now, since we have assumed the magnetic field is to be uniform, so this quantity will vanish because del of B, this quantity will vanish, and what we have is only del B by del T. So therefore, this equation here, it will be del B by del T. Let us note down this equation. So we have the change in the magnetic flux encountered by the moving loop will be d phi by dt will be a sum of these two integrations. The first integration is del B by del T dot ds plus surface integral over B dot d by dt of ds. So let us try to find this integration one by one. Let us consider the first integration, that is surface integral of del B by del T dot ds. Fine. So to start with, let us consider some simpler equations which we all know from the electrodynamics. That is, first one I am going to write as the Ohm's law, which says my current density J is equal to conductivity into E plus V cross B by C, where E is a field and V is a velocity. And then we will have the Maxwell's equation. The Maxwell's equations are, the first one is curl of E is equal to minus 1 by C into del B by del T, and curl of B is equal to 4 pi by C J, where J is the current density, plus 1 by C into del D by del T. So now let us we will consider the scale in which we are looking at the plasma. The plasma is neutral. That means there is no space charge, so there won't be any displacement current. So this portion I can always neglect it. So then my del cross B will be 4 pi by C into J. And then the other equation is, we know, it's a very easy equation. Del dot the divergence of B is equal to 0, and finally we have del dot of displacement current will be equal to 4 pi rho. Anyway, we don't need these equations. We need only these 4 equations. Let me write as 1, 2, 3, and 4. So from here, okay, so let me, from using this equation, from here I can write my E is equal to J by sigma minus V cross B by C. And if I substitute here the equation 2, so what we are going to get is, this minus I will take here, so we are going to get 1 by C into del cross V cross B minus 1 by sigma, correct, minus 1 by sigma into del cross J. Correct? Yeah. And that will be equal to 1 by C del B by del T. Okay, so now from here I can express J as C divided by 4 pi into del cross B. So let me substitute for J here. So this is going to be, I'll put it, first write the, let's say 1 by C into del B by del T is equal to 1 by C into del cross V cross B minus, so this is going to be, J is going to be this, so C divided by 4 pi sigma, C divided by 4 pi sigma into curl of P. So now we know curl of B will be equal to divergence of del dot B minus del square of B. So we know from the Maxwell's equation, this goes to 0. So this is going to be only minus del square of B. So this term will become minus del square of B. So this minus becomes plus. So we will have del square B. And if I take the C here, cancel the C everywhere. So what we are going to get is, this is going to be C square. For a plasma, the conductivity is very high. If we assume the sigma tends to infinity, then we can neglect this term, and then the del B by del T will be curl of V cross B. So therefore, this equation is going to be surface integral of curl of V cross B dot ds. Let me note down here. So this first integration, that is surface integral of del B by del T dot ds, will be surface integral of curl of V cross B dot ds. Cool. Now let us look at the second integration, that is b dot d by dt of ds. Now this term is nothing but the evolution of the surface. So let us assume or let us denote our original surface as S0, and after time dt it is evolved to a new surface, let it be S1. So we are having an infinitesimal surface selected at S0, which is ds0, and an infinitesimal surface selected at S1, which we call as a ds1. So now this trajectory of this loop is going to create a cylinder. Now we know the vector area of a closed cylinder, surface is 0. It is simple because if you assume a cube, and if you try to add up the vector area, all the opposite sides gets cancelled off. And similarly, you can do it for any closed surface. You will see the opposite vector area, opposite area will get cancelled. Therefore, the total surface area, so total vector area of a closed surface will be 0. So now here, if you see, so we again here in the cylinder which we are considering, so we are having two circles at the bottom and the top, and a curved cylindrical surface. So the total vector area of all the surfaces has to be 0. So we will consider the direction outward direction. So now if I take all these outward directed vectors, if I add them up all, that has to come out to be 0. So now if you see if I take the direction of the loop and the surface direction as, if my S1 is outwards, then my S0 is inwards. So when I add up these two areas, what we will get is ds1, that is infinitesimal in the S1, added to the second surface, that is ds0. Now ds0 is inverse, so you have to take the opposite of it, so it makes it minus ds0. And now we have to go for the curved surface. So if you see, the length of the curved surface will be vdt. So now let me consider a small element on the side of this curved surface, and let me denote the length by delta L. So then the area of this element will be v dt cross delta L, or I can write it as v cross delta L into dt. Now if you see, v cross delta L is again inward. So if you want to take the outward direction, and then you have to add up. So if you want to take it outward, this becomes negative. So therefore this is going to be v cross delta L dt, and this sum will be equal to 0. Therefore, ds1 minus ds0 will be equal to v cross, sorry, I have to take the, I have to integrate over the whole curved surface, so there will be an integration. This integration will be over the infinitesimal size ds1 or ds0. So let me denote it by say something r. That's a smaller ring I am going to say. So will be equal to v. Let me take the dt outside. V cross delta L. So integration over delta L, I can take the dt outside. Now this is nothing but, this is the evolution of the infinitesimal surface over the time, the dt. Am I right? So this is nothing but d of ds. Am I right? So now, so therefore, d by dt of ds will be, when I take d by dt, is nothing but the integral over the region R into v cross delta L. So this integration is going to be, I'm going to have we have already an surface integral, and then this integral over the infinitesimal surface ds1, and b dot v cross del L. Now if you see this line integral, that's over the infinitesimal surface ds. So now, and then I'm going to do another integration over the S. That means this integrations, I have to do all these integrations over the whole surface, which eventually means, is I'm going to get the total outer, is the integration will be equal to the integration over the outer contour of the surface S. So I can write this as my integral over C, that's my over the whole surface S, into B dot V cross, now I will not call as delta L, I will call as dl, because this is an element on the outer surface, the main surface. So now this is there. So now let me try to do some jugglery here. So we can always write this cross product as B vector dot V cross dl. We can use the cyclic property and we can write it as dl dot B cross V. Okay, so I can write this as minus V cross B dot dl. So this will be, so I can write this equation as, so this is going to be V cross B dot dl. Sorry, there's a minus. Now if I use a Stokes theorem, so we know line integral over closed over the surface, f dot dl will be surface integral over curl of f dot ds. Okay, so here f is nothing but v cross b. So this will become, so therefore my surface integral over b dot d by dt of ds will become surface integral over curl, sorry, minus is there, curl of v cross b dot ds. And this is, and addition of, you can see this plus this is nothing but will be 0 because they both are just opposite signs. So we are having, so therefore what we get is, we got our answer, that is d phi by dt is equal to 0 or phi equal to constant. That means as the plasma moves along, the flux carried by the plasma is going to remain constant. That means the plasma is going to freeze the magnetic field and is going to move along. Now if you remember, we had an initial assumption that the magnetic field is uniform, but it is not necessary. Even if the magnetic field is non-uniform, still the plasma can freeze the magnetic field and carry on. So that derivation is slightly complicated, and interested readers can refer the paper which is mentioned in the description, where they have done for the case of that where the solution they provided, it shows even for a non-uniform magnetic field, the magnetic plasma freezes the magnetic field. Well, now if you consider the situation, so the plasma is freezing the magnetic, frozen in magnetic field, and as it move along. Now if I start compressing the plasma, so as I compress the plasma, these field lines are going to be brought closer to closer. So as they get closer and closer, at some point the field lines start merge and then they annihilate. So we know the magnetic field have an energy. So the magnetic energy density is given by b squared divided by 8 pi. So in this annihilation, some magnetic energy is lost. This lost energy is dumped on the charged particle in the plasma, and the particle gets accelerated. And this type of acceleration is called as acceleration magnetic reconnection. This process is called as magnetic reconnection, and we will see how this magnetic reconnection happens and the different terminologies and how the plasma gains energy in the next lecture. Thank you.